Welcome to this lecture on Neutrosophic data, mean, and variance. In this session, we will explore a modern extension of classical statistics that is designed to handle uncertainty in a more realistic way. In traditional statistics, we usually assume that all data values are exact. For example, we might say that the temperature is 25 degrees, or the travel time is 30 minutes. However, in real life, such exact values are often not available. Many real-world situations involve vagueness, imprecision, or incomplete information. For instance, the temperature might be somewhere between 20 and 25 degrees, or travel time might vary between 25 and 40 minutes depending on traffic conditions. To deal with such situations, we use the concept of Neutrosophic data. This allows us to represent data not as a single fixed number, but as a range of possible values, capturing the uncertainty directly. In this lecture, we will focus on three main ideas. First, we will understand what Neutrosophic data is and how it differs from classical data. Second, we will learn how to compute the Neutrosophic mean, which represents the average when data is uncertain. Third, we will study the Neutrosophic variance, which measures variability under uncertainty. We will also connect these ideas with daily life examples so that the concepts become intuitive and easy to understand. By the end of this session, you will see that classical statistics is actually a special case of Neutrosophic statistics, where there is no uncertainty in the data. Now let us understand what Neutrosophic data actually means. Neutrosophic data refers to data that contains some level of uncertainty or indeterminacy. In simple words, instead of having a single exact value, we represent the data as a range of possible values. For example, consider temperature. Instead of saying it is exactly 22 degrees, we may say it lies between 20 and 25 degrees. This range reflects uncertainty in measurement or environmental variation. Similarly, monthly expenses may not be fixed. A person might say their expenses are between $30,000 and $35,000. Travel time is another common example. It may vary between 25 and 40 minutes depending on traffic. So, Neutrosophic data allows us to model real-world situations more realistically by capturing this uncertainty directly, instead of ignoring it. In this slide, we compare different types of data. First, we have crisp data. This is the type of data used in classical statistics, where each value is exact. For example, 30 is a precise value. Second, we have Neutrosophic data, where values are given as ranges. For example, 25 to 40 represents uncertainty. Third, we can also have mixed data, where some values are exact and others are intervals. An important point to understand is that any exact value can be written as a range where both limits are the same. For example, 30 can be written as 30 to 30. This means that crisp data is actually a special case of Neutrosophic data, where there is no uncertainty. Here we see how Neutrosophic data can be visualized. Each observation is represented by a vertical line instead of a single point. The lower end of the line represents the minimum possible value, and the upper end represents the maximum possible value. So instead of plotting a single we plot a range. This gives a much clearer picture of uncertainty in the data. If the line is short, it means the uncertainty is small. If the line is long, it means there is more uncertainty. This type of visualization helps us immediately see how precise or imprecise our data is. Now let us move to the concept of the Neutrosophic mean. In classical statistics, the mean is simply the average of all values. In Neutrosophic statistics, we follow the same idea, but we work with ranges instead of exact numbers. We first add all the intervals together and then divide by the number of observations. Let us take a daily life example of travel time. Suppose on 3 days, the travel times are between 20 and 25 minutes, between 25 and 30 minutes, and between 30 and 40 minutes. When we compute the average, we do not get a single number. Instead, we get a range that represents the possible average travel time. This slide explains how to interpret the Neutrosophic mean. The result we obtained is a range rather than a single value. This means the average is not fixed but lies somewhere within that interval. The lower bound represents the best-case scenario, while the upper bound represents the worst-case scenario. In practical decision-making, this is very useful. For example, if you are planning your travel, you may consider the upper bound to avoid being late. If you want a rough estimate, you may take the midpoint. So, the Neutrosophic mean gives more information than a single number. In this slide, we visualize the Neutrosophic mean. The dashed lines represent the lower and upper bounds of the average. These lines show the range within which the true average lies. This visualization helps us compare individual observations with the overall average range. Instead of thinking of the mean as a single line, we now think of it as a band or region, which better reflects uncertainty. Now we introduce Neutrosophic variance. Variance measures how much the data values vary from the average. In Neutrosophic statistics, since both the data and the mean are uncertain, the variance also becomes a range. A small interval in variance means the data is consistent and stable. A large interval means there is high variability and uncertainty. This is especially important in real-world situations where risk and uncertainty must be considered. Here, we apply the concept of variance to our travel time example. We already have the data as intervals and the mean as a range. When we calculate variance, we again obtain an interval. The lower bound represents the minimum possible variability, while the upper bound represents the maximum possible variability. This gives us a complete picture of how spread out the data might be under uncertainty. In the next slide, we will see what people do wrong things in Neutrosophic computation. In this example, the computation of variance is not fully correct to show that people do this practice in their calculation, which is complete wrong and against the rules defined for Neutrosophic numbers. Here the variance has been calculated by treating the lower and upper bounds separately using classical formulas. However, this approach does not follow the proper algebraic structure required for interval or Neutrosophic data. In Neutrosophic statistics, interval values must be handled using appropriate interval algebra, where uncertainty and indeterminacy are preserved throughout the computation. Simply applying classical variance formulas to the bounds leads to misleading or incomplete results. For accurate and theoretically consistent results, we recommend using the Neutrostat, our package. This package is specifically designed to handle Neutrosophic data and performs computations, such as variance, using the correct algebraic framework. Therefore, instead of manual calculations, it is more reliable to compute Neutrosophic variance using the Neutrostat package in R. Here I will also say that people just use classical results with subscript n to show that it is now Neutrosophic, which completely wrong. I will suggest study first Neutrosophic algebraic operations first to see behaviors of these results in Neutrosophic framework. Thank you for watching with Dr. Zahid. Do not forget to subscribe my channel for more informative videos on modern statistical methods.